Hello there. We're going to continue designing this buck converter. This is going to be a buck converter board with three different voltages, three different voltage outputs. And in this video, I'm going to be designing the 12-volt variant. There is a link below the video that points to the GitHub account, the GitHub page, where you can download the schematics and all of the design files for KiCad. This is a converter based on TPS54360 buck converter chip, and the design procedure basically involves just calculating all the components around it to ensure that it works perfectly on given the input and the output voltages that are desired. We are designing this to accommodate for 48 volt input voltage, although the maximum input voltage of this chip is 60 volts. So let's get down to it and copy this block here. Let's see. I don't want to drag it, I want to just copy it. So copy block. And then we'll put it, oh no. Let's see. Did it just screw up completely? Let's see. So if I drag this, if I move this thing, okay. So I can move this thing and it doesn't seem to have copied the rest of the components. So we'll copy block. Really? Wait, I think I'm doing it wrong. I think I have to do like this. Let's see. I have to do like this. And I have to, no. I have to do like this and then I have to duplicate it. Duplicate block. That's it. Okay. So we'll place this block here and we will move this text here to signify that this is a power supply of 48 to 12 volts. So now we can go into the details. And the details are presented in the datasheet of this converter. And there is a full application note of the example application, which I'm following pretty much to the point. And the only difference is the values of all the components. So we're going to calculate the values of all of these components, given the input voltage of 48 volts and output voltage of 12 volts. The first thing we need to do is select the switching frequency. Now the switching frequency depends on the input voltage, and I think it also depends on the output voltage. And what I've done here is I've set up a design document where I put all of the values for the selected input and output voltage. So we have 48 volts, we're going to add a new line here, 48 volts in and 12 volts out at 3.5 amps. Now, maximum skip frequency. The way that design document says you should calculate this is you should calculate the skip frequency and the shift frequency and then choose the highest one of these. Let's see, just to make sure. Right, no. You're supposed to, sorry, you have to choose the lowest one. So we can start here by making this calculation. So it's 1 divided by, actually I can go back here. I think I have the calculation here somewhere. So I can go to 1 divided by 335, 50, 3.5, 25, 607. This is the one, and we'll just replace this with 12 volts. And we're using 50 volts as the input, just to have a little bit of margin there. It's 92, 07, 50, great. So At 12 volts, our switching frequency for this max skip switching frequency is 1.8 megahertz. So we're going to put that there, and we're going to calculate the second value. The second value is, let's see, I just forgot my camera, I think. Oh, hi there. So this is going to be on top. There we go. The second one is calculated using a similar formula, which I also have here somewhere, from the previous design, and it's using 8 divided by 135 nanoseconds. So it's going to be this one. So it's 4.7 amps, 0.1, 0.7, and then we'll use 50 here, and we'll use, so this is just based on this output voltage, or input voltage, sorry. So this is going to be the value we get for the lower limit. So for this design, we basically end up with the same values for these frequencies. We can basically just choose 960 as we did on the previous designs. We can have the RT set to 100K. So, next thing we're going to do is choose the inductor. The formula for choosing the inductor is specified here. So this is the minimum inductor value. We're using 5 volts. So we're going to enter we're using 12 volts for our design. They're using 5 volts for this example design. So we're going to enter 12 volts instead of 5 volts here. We're going to enter 50 volts instead of 60 volts here. So let's see if we have this calculation somewhere. So 50 minus 6, we replace with 50 minus 12, 3.5, 0.3. 6 divided by becomes 12 divided by 50 times 960. So this ends up being 9 microhenry is the minimum inductor value, which is a little bit bigger than our previous inductors. So we're going to have to find an inductor. We can start with our current inductor, which we have here. Just going to copy that number, and I'm going to go to Mauser. I'm going to search for that article number. And what we can do then is just search for similar inductors. So I want to have the same footprint. I want to have basically everything the same besides the inductance. So I want to have also 4.5 amps, which doesn't give us any products there. So we can possibly, let's see, if we go like this. Probably it's just better to search for the current, and we can see if we can find anything that is similar. 7.2 times 6.5. It's 6540 is the package. I wonder if this is the only inductor that has that package. It certainly seems that way. Should probably choose like 10 microhenry. Okay, fair enough. We have something that is very similar, but I'm gonna go ahead and find something that they have in stock. So I don't want to choose something that has 255 items in stock. That's just too little, or 69. That's nothing. More like 2,000, or if we can find something that they have even more in stock of, then we can choose that. And this seems to be one of the inductors that they have in stock, which is one of these, but it seems to be a little bit high. I don't want to have an inductor that's too high. So I want to be able to like stack those boards together, and I don't want the inductor to like stick out too much on the top. So at 10 microhenry, it's gonna be so it seems that they all have pretty much the same size. And do they have any number for the package? I really don't like choosing a package that doesn't have any number. Mainly because I want to have something that is more standard, that is not like something I have to make a footprint for. So like this is 8040. Okay, 8040 is a standard package, so we can check this. Even though they have 700 in stock, it's something we could actually use. And this one is actually lower, so it's 4 millimeters instead of 5. Okay, this looks interesting, but what I'm gonna do is go back up here, and I'm gonna just search for inductors that are not just 10 microhenry. I'm gonna search for 12, 15 microhenry and see if I find anything. Let's search for. So we've got just quite a few of them. Let's have a look at the maximum currents that we're going to be generating in this inductor. So we've got, the calculation tells us that our inductor has to be 9 microhenry at least. We could say like 9.1 microhenry. We don't know which value we're going to choose, but we're going to like just try to calculate as many values as we can here. Maybe we can use, for example, 10 microhenry and see what would be the maximum current. So we need to know the inductance in order to calculate the ripple current and the peak current. So it's going to be 0.95 amps. If we choose 10 microhenry, let's see. The ripple current is going to be 0.95, and maximum current is going to be the ripple current divided by 2. It's probably going to be something similar here. Like 3.5 is the rated output current plus 0.95 divided by 2. It's like 3.97. So we don't want to choose an inductor at that is rated at 4 amps. We want to choose something that is bigger. So we go back here and we can actually deselect that, and we're gonna search for anything between 4.2 amps and maybe 5 amps, because I wanna find as many inductors as possible, so we don't have to like just choose from a very limited selection. I want to go and see if we can find something that has a good footprint that they have in stock. And as you can see here, if we start at like let's say 4.2 and all the way to like 4.9, 4.8, probably don't want to choose anything above 4.8, but up to 4.8 there's a lot of different values there, and we can search for all of them, and we have like 594 inductors to choose from. And then we pick the inductance at 10 microhenry. So we got 53 to choose from. Right. And we can also choose SMD. So we don't want to have through-hole inductors. Actually, I don't want to have any through-hole components. I hate through-hole components. Like, it's so much easier to work with SMD components. It's so much easier to even solder them. Usually when I order, when I do some prototypes and I solder them manually, I order for like 2 or 3 prototypes, and then I actually solder them all at the same time. And I don't even have to pick the board up if I use SMD components. With through-hole components, I would have to pick the board up and I would have to solder on the other side of the board. And I would have to like hold the component with my fingers just to make sure that it stays in place. With SMD components, I just don't have to do that. So SMD components are just so much nicer to work with. So I'm gonna go up here and I'm gonna sort them by price, and hopefully we can find something that they have in stock, like this one. So this looks perfect. Like this is a big inductor, and it has a standard footprint, 1005, and it's 10 microhenry, but it looks like it's a little bit big. Okay, this one is quite big as well. You know, they're getting quite big at these ratings. Let's see, 4.4 amps. So like there are just very few inductors that they have in stock that are kind of standard inductors. For example, if we look at this one, this was like 11 in stock. Definitely don't want to buy that. So it almost looks like we have to choose this inductor. Come on. Okay, let's see here. So this is a 1005, and it's basically 4.5 millimeters. And it is, let's see, five millimeters maximum. Okay. So there's one important thing to look at here is that there is a tolerance of 30%. So if you choose an inductor and you have like 9 is your like desired inductance, it's probably this is not good. You know, like if we choose a 10 inductor and it happens to be 30% minus, we only have like 7. I didn't even have to calculate it, by the way. Could have calculated that in my head. But this definitely seems like not a good choice. Let's try 12. Okay, this looks good. This one is 20%. It's within our tolerance. And it's 6 millimeters high. And is this a 5 amp? 4.6 amp. Okay. Well, we can go with this one. This one seems definitely good. And there is really no other choices here besides probably this one. How many did they have? Oh, they don't really have that in stock, so nah. And I don't like this type of inductor that is exposed. These ones are nice, but then are there any other ones? There are no other inductors that they have a lot of in stock, so let's go with this one. So we're going to go with a 15 microhenry inductor. And this comes in a package that is called 50/50. It's like 12/12. So this one is 50/50. Let's recalculate the values for this inductor. So we have our ripple current, which is supposed to be like this. That's 10, that'll be 15, 0.63. Microhenries. Yeah, 0.63. And maximum current so the maximum current is calculated by first we take the RMS, That's 50 and 0. Let's see. $15. I think this is the right calculation. Okay, yeah, we end up with 3.5 amps there anyway. So then we can go and calculate the peak current. So the peak current is going to be 3.5 amps times 0.6333 divided by 2. Wow! Is that even true? Let's see. Did we do this right? So this was 0.82. That's 6 volts. Okay, something is really wrong here. This is the wrong formula. Okay, let's see. Let's recalculate it. So it's 12 times 50 minus 12 divided by 50 times 0.0000015 times 960,000. 0.63. Okay. So what did we get here? 0.67, right. So that seems to be correct with at least with the calculation we did here, right? 0.67. Okay. And then if we do 3.5 times, let's see, 3.5 times 0.67 divided by 2. Interesting. Oh wait, that is plus. That is plus. Right, that explains it all. Okay. So yeah, we got 3.8. 3.8 amps, which is like close to 4. It's perfectly fine if we just choose an inductor 4.2. Okay. So let's see. 3.81. We can take this inductor and we actually have it, I think, already. Yeah. Okay. So we got the inductor and we can go to the capacitor, to the output capacitor, which is supposed to be, let's see, so if the change in current is larger, this value is going to be larger. So this is basically dependent, like capacitance of the capacitor is only dependent on the current change of the output. So we can probably leave the capacitors the same, but there's also this current on the capacitor, which in the last video we've concluded that it was rather hard to figure out exactly what current we could use on the ceramic capacitors. Like on aluminum capacitors, you get this value in a table in a datasheet. But for ceramics, it seemed that like they had very good performance in terms of the charging currents and everything else. So we can probably, for now, like just leave this out and use the same capacitors that we've used for the 6 and 5 volts, which are 47 microfarads. The only thing is that now we have to increase the voltage on these capacitors. We don't need to increase the voltage here, and we don't need to increase the voltage here, but we need to increase the voltage on the capacitors here. So we have to make them 47 microfarads, probably 16 volts. And what I'm going to do is I'm going to go back here and I'm going to pick the capacitor that we've chosen for 47 microfarads, and I'm going to just search for that capacitor, and then I can search for similar capacitors. So I can search for X5R and 47 microfarads, and I get 79 choices, and I can choose for the, I can pick the package, and the only thing left is the voltage, which does not go above 10 volts in that package. So let's remove the package. Now we can choose from 79 products. So we show similar ones, and we can go here up to 25 volts. So we choose 16 volts. And we have 11 alternatives. So what we have here is an MLCC in X5R in 1210 package, which is good. We can pick that one. And in fact, what I want to do is I want to take all of these capacitors. I want to replace them with the one that we've chosen, because it's very nice to be able to reuse the same part on different in different places on the same board. So we'll use this capacitor in 1210 is the package, 16 volts, and we're gonna replace all of these. So this would be 16 volts, and this would be 16 volts as well, and then we're gonna go up here also. This would be 16 volts as well. One of the functions that I'm really missing in KiCad is the ability to change a value of different parts in one step. So it would have been so nice if you could just search and replace, or at least like search for parts that have this value that we just changed, and then get them highlighted, and then just be able to change the value. That's something that Altium has, and that's very nice functionality. Okay, so that is done. And then we're gonna go and check what we have next. Catch diode. So this diode is gonna be the same, it doesn't really matter. Input capacitor is gonna be the same. Bootstrap capacitor is going to be the same. Under voltage lockout set point is going to be the same, because we're not changing our input voltage. And let's see, voltage feedback. So next is the output voltage feedback. This is important. So this sets the voltage, the output voltage of the regulator. So if we use the 10, they've used a 10.2 kilo ohm resistor, and the main reason for that was because they could get the high side resistor here, to a value that is easy to find, that is a common resistor value. So both like on the 6 volts, we got that to a common value, and on the 5 volts, we got that to a common value using the 10.2K. We can try to get it to the same, to a common value even here with 10.2K by using the 12 volt output, and we'll see if we get it to some common value. So 142,800, 142.8K. I think that is something we can find. Let's see. This is in Swedish, so if you're an English speaker, you probably don't understand what it says here, but I do my best to explain it. Let's see. So we have resistors, and we can go here, and we can see, like, can we choose a resistor that is 142K? And I'm pretty sure we can choose something that's very close. It's like 142.2 is one, but like 143K. That's what we're gonna go with. And we want to have, no, we don't want to have 603 in millimeters. We want to have 603 in imperial units. There we go. It's 143K. 0603. I'm going to sort that by price, and I'm going to choose the one that they have most in stock of. Okay, it's still loading. Okay, the stream is not doing very well, but we'll try to continue, and we'll see if it's gonna turn out well. But I seem to have lost my internet connection. Let's see. Can I get my internet connection back? Okay, so the stream has stopped on YouTube. Hopefully it's going to get back soon. Okay, it seems to be back now. Let's see. So we got these ones, we got these ones, we got, what else? Like all of the others, they're just not stocked. Panasonic. I'm gonna choose the top one here. So I'm gonna choose the one from Burns, and I'm gonna put it here. So this will be 143K, 1%, 0603. So that's our output voltage selection. Minimum V in, we don't need to calculate. Compensation. Compensation is dependent on the voltage, so we have to do that. We have to at least try to do this calculation. So we can go 3.5 divided by 2 times 3.14 times 12 in this case, times 58.3, but that is going to be like this, so it's going to be like 0.000 0. like that, I think. So it's 796, which looks a little bit weird. Let's try this with 5. Right, okay. So 796 is the frequency. The pole frequency. And the next one is the zero frequency. So I'm going to calculate that as well, and that is going to be actually the same. That's going to be exactly the same as for all the other designs, because it's not dependent on any voltages, it's only dependent on the output capacitance. They choose 58.3 here because this is a derated value. They specified here this is a derated value of 58.3. This value is going to be exactly the same. Now, what are we going to do here? Do we need to choose the biggest, the largest one, or the smallest one? Let's see. To determine the compensation resistor, assume use equation 48. So I guess they kind of choose the smallest one. But I have to check. So let's see. Assume. Let's see. Use the lower value of equation 46. So this is equation 46. Equation 46 and equation 47, right? So we have to use the lower value here. And what we're going to do is, we got our value of 796 here. So we're going to take the square root of, let's see, square root of 796 times 1092,000. That gives us 29. And then we're going to take square root of 796 times 960,000 divided by 2. This was 19. So I'm going to use 19.546, which is the lowest value of these two, to calculate our resistor value, which would be times 58.3, which is again in microfarads, so we're going to do like this. 2 times 3.14 times that value. I'm taking this equation from here directly, so this is the equation I'm using. And then we're going to take and divide that by 12. So this looks weird. Did we get this right? Oh, so we have to divide it by 12, and then we have to multiply that. So this is the first we have this part. Then we're going to take and multiply that by 12 is our output voltage divided by 0.8. See, 0.8 times 350, 0.000,350. Like that. So we get a value of 25.5 K for this resistor. 25.5 K. Right, and then we need to calculate the capacitor, C8. We're going to have to choose the largest value of these two. So it's like 58, let's see, 0.0058, no, 0583 times 0.0025 milliohms, and then divide that by 25,500. That gets 0. Okay, so the calculator cannot calculate values that are so small into the picofarads. So we're gonna like multiply that by 1,000,000. So let's do this. Multiply that by 1,000,000, we get 5.7 microfarads. So we can deduce from this that the capacitor value should be 5.7 picofarads. Picofarads for this one. And then we have to calculate this one, and we're going to choose the biggest one. So we go back here and we take 1 divided by 25,500 times 960,000 times 3.14, which is 0 again. So we have to take and we have to multiply this by 1,000,000. Like, it's totally fine calculating a value, like intermediate value here, but when it comes to results, it doesn't show you the result if the value is too small. So this would be 13 microfarads, so we can conclude that this is supposed to be 13 picofarads. This was 5.7 picofarads, by the way. So if we take this one, it's 13 picofarads. So we're supposed to choose 13 picofarads for this capacitor, C8. And that is like, so is that like maximum value or what? Right, so they choose a little bit smaller capacitor. So let's choose 13 picofarads. And let's try to find a capacitor that we can use for that. So 13 picofarads, it doesn't sound like it's a standard value. I want to have the ones that are 0.082 euros. Okay, well, that's fine. So it's like 50 volts. We don't need 15 volts. With 50 volts, we can take 10 volts. And we can also take 603. God damn it. I hate it when the page jumps the moment I am about to click on it. Let's see, so 0603. This is the ones that we need, so X8R. It's a very exact one. 13 picofarads. Zero 0603. Now I want to calculate the capacitor C5. C5 is calculated by taking 1 divided by 2 times pi times 25,500, which is the resistor value we got earlier, and then you use this frequency, and the frequency we got is 796. 796. Wow, that's interesting. Let's see. So we got 7,800 picofarads. And remember, it's okay to choose a capacitor that is larger. So we can choose 8,000 picofarads. That is very strange. There are no capacitors of this capacitance. Why not? Let's go back to the capacitor selection. So we remove this search term, and we can use 603, and then we just search for 10 volts. Let's see. And then let's see if we can find something that is close to that. So there is 8,200, which is better. Right, so we can choose the 8,200 safely because they have chosen a capacitor previously that was they've got 6,400 as a minimum value here, and they chose 6,800. So we can easily like choose 8,200. Now that looks much better, but they are not in stock. And quite unfortunately, you cannot actually select that. I only want to see components that are actually in stock. Look, you have to scroll through the whole thing here and look for components that are in stock. And they are not in stock. There is like 52 weeks. You have to wait. Look, you have to wait 52 weeks, like a year, before you can get them. That is ridiculous. Look. None of them are in stock. That's really bad. Besides this one, and I don't want to choose something that is like, I don't want to choose this unless I really have to. So I'm gonna go ahead and I'm gonna remove this DC voltage rating, and I'm gonna see what we find. And I think we're gonna find a lot more capacitors, and we can probably choose some that is rated like 16 volts or something. Like here, check this out. So this is 50 volts. And they have plenty of those capacitors. Like, we don't need to even choose something that is rated at a lower voltage, because we can get this, and this is the package that we want, and this has like everything. It's very exact. It's X7R. We were searching for X5R. So let's just go ahead with this. This is perfect. 20%, 10%. Let's go with the 10% one. 8,200 picofarads. I'm going to write 10 volts here, or actually I'm going to write 50 volts here. And I can actually put a note that says that so what is next? Power dissipation estimate, discontinuous conduction mode and echo mode boundary. Power dissipation estimate we don't need to do right now, and that's it. That's pretty much it. So now we got the schematic, and we need to just add an input plug that is gonna connect the battery voltage to all of the regulators, and we need to annotate it, and we need to create the PCB. So let's go ahead and just so what I'm gonna do is I'm gonna annotate this schematic. I'm gonna add all of the required components. I'm gonna export the netlist and create the PCB and place the components roughly where they should be. And after that, I'm going to go back to this schematic and I'm going to review it. So I'm going to go through every single connection here, and I'm going to just double check with the datasheet that everything is correct. Because as you remember that when we started designing this part, we actually discovered that some of the components here were just copied from another place and they had wrong values on them. So it's quite likely that some detail here is wrong. So we don't want to just go ahead and produce this unless we know that it's correct. So it's always good to review a schematic after it has been done. It's useless to do a review until all of the components are placed. So we're going to go ahead and just try to make sure that all of the components are on the schematic. And then after that, we can do a full review of the schematic. Right, so first of all, I'm going to go and annotate this schematic. How do we do, let's see, so we can run this and we can annotate, we can sort them by Y position. And definitely this looks more reasonable than the X position. Like, why do we go like this? Like, this is bad. It's better to go like this, so everything's going to be numbered like this. Keep existing annotations. Sure, we don't have any, so. So we got this CVPCB now that has all the footprint assignments, etc. This is going to be part of the review to actually also assign the footprints. We can do that later. So what else do we need? We need a connector, and I want to use one of these XT connectors. And I'm thinking that maybe for the output we could also use an XT connector, but that's something that I'm just considering. We can either use an XT connector, or we can use a pin like this, which we will assign a pad footprint to. So this is going to be like a pad which is possibly 3 to 5 millimeters wide, and it's going to have a lot of VS in it so that the heat can escape on both sides of the PCB. I'm just curious, like what can we use for the power connectors, and definitely probably for the battery we would use an XT connector. I want to see what we have. We could use the XT60, which is the standard. Let's see. Let's see if we can find the XT60 on Mauser. Oh, look at that. So the XT60 is a plug that we probably don't have a footprint for it, but we can create one. Let's see. I find it quite interesting that those connectors come from SparkFun. That's a pretty good data sheet. So what is the diameter of the plugs? What is the diameter of the pins? Like the most important thing, the most important thing that is of interest, they don't actually show it. This is a totally useless data sheet. I want to see the footprint of this connector. Let's see, XT60 footprint. What is the diameter of the XT60 plug? Look, here's somebody who's been doing a PDB. Like this is not good. I really don't like that kind of mount. You know, like you solder them up like that, and then they fall off when you plug the cables in. Really stupid. Okay. Does this say something? Well, this is good. This has at least the distance between the pins. But this is something else. This is not even the. This is not like this is XT30. This is not XT50, XT60. What is this? XT60 KiCad footprint. Okay. Looks interesting. So they're 4.5 millimeters, and there's 7.5 millimeters between them. Well, that's nice. Let's just download it then. Okay, fair enough. We can copy this one. Let's do like this. Let's open this up. Cool. What the hell? Like, why is it so... Why did it end up with empty lines? Yes, I know. I should have used a regex for this, but I just can't bother. Let's see. So that's good. We'll see later if we can load that footprint, but for now we can just add a connector for it. So this would be a con 0. Let's see. Okay, that's fascinating. So do we not have any libraries loaded? Okay. Do I have to modify this every time I start KiCad? This is really interesting. So this is version 5 of KiCad. This is like a bleeding edge version. So it's definitely it's not stable. So every time I start this, I have to actually add the libraries, I think. See, where are connectors? We're supposed to have the connector lib, but okay, so the problem is that this path is not populated, right? So for some reason, it doesn't populate that path. Why? KiCad sys symbol there. Okay. Right. Oh my God. Does it use like, oh, this is ridiculous. Okay, let's see. because what I did is that I moved this schematic from a different location. So what I think happened is that it was expecting it was expecting the schematic to be in a different location. Let's see. They really have to fix this in the final release of KiCad 5. Let's see, drone power supply V2 Pro. Does it save the location? No. Okay. No, I don't want to create it. Like, fuck off. What is this? I want to open my schematic, and I don't want the schematic to be in that location. I don't want, like, I want the schematic to be under schematic. I don't want it to be under drone power supply version 2, drone power supply version 2, schematic, blah, blah, blah. Like, I want to open this file. Come on. What is this? Okay, I can open that file, but I cannot open it. I cannot click here. Oh, now I can. That's fascinating. Okay, there's clearly some problem with this in this version. Okay, let's go back there and let's see if we can add our... No, we can't. Okay, we cannot add the device. I'm supposed to be able to do that because I have the connector lib. Actually, I have all the libraries. Like I have, but this path is not populated. I'm gonna restart KiCad. Wait. Let's see. So I'm gonna restart the whole program. Could it be just because I've changed the directory name? It shouldn't be. Maybe I should configure paths. Right, so what I'm gonna do is go to the main KiCad window and I'll copy this path. Oh, it's not even there anymore. Like, this is ridiculous. What the fuck? Okay, let's see. So I'm gonna go back here. I'm gonna try to re-add this path. Okay, so this would be KiCad sys symbol dir, I guess. And then we're gonna click OK. And do we have all the libraries now? Okay, at least that one seems to be set. And then we can click OK, and then we can see if we get right. So it loads all the libraries. Great. So and then it comes up with this error dialog. So it says like valves.lib could not be opened for reading, and this is because you just have to add all the libraries manually, and sometimes when you have files that have like different case in the name, like if valves is called valves with a capital V in the beginning in the Git repo for the libraries, then KiCad cannot find that library because it is defined to be with lowercase v. And I just don't get why they have to do it that way. Why can't they just load all the libraries? So we're going to use a connector of 1 times 2. And then we're going to have battery. We're going to connect the battery. We're going to assign the XT60 footprint to this later. Let's see. So this is going to go to VBAT. And number 1 is going to go to ground. Right. I think that was a 10 times 10 and a half. Was it not? The one that was 100. Oh crap, I forgot to even add that one. Okay. So I have to choose I want to find that SMD capacitor that I've found previously for 100 microfarads. I think it was the one that was like 10 times, could it have been this one? 10 times 10 times 10 times 10 and a half. Now I cannot find it. Oh crap. So there's also like the height of the capacitor. You can see it here. It's 12, it's 10, 10, 10, 12, 12. So it's like I mean, preferably I don't even want to use this. I want to use something else. I want to use like I want to use a film capacitor or a ceramic capacitor. Like a larger one, because I really don't want to be 10 millimeters off the ground with this one. Okay, let's leave it for now. Let's go and set these ones. So that's 603. 2.2 is 603. 603. Let's see. Oh, there it was. That was the capacitor. I actually didn't move these ones. I had to move it down here. Insert rows below, and then we just place them here. .2 microfarads, 63 volts. Do we have that one? I think that what we have done actually is that this capacitor is not 2.2. Yeah, they are actually 2.2. Okay, because I have a 4.7 in the list. I think I added a 4.7 instead of 2.2. This one X7R. Do I remember the reason for doing that? Or was it just because I found that capacitor? Let's see. So this has to be. So we have film capacitors, right? I think the point was that this 2.2 was not actually available in ceramic form for some reason. So what I chose was a 4.7, and I mean that's fine. Like 4.7, we can have more capacitance for that. It's in 2320. 4.7 microfarads, and the reason it has such a large case is because it's rated at 63 volts. We can safely increase the input capacitance. It's just better. It just improves the performance and decreases the input voltage ripple. Let's see. So now we can go back to this, and then we can do. Did I just lose? Did I just lose my assignments? Like seriously? God damn it! Was it because I didn't save it? Oh, crap. Okay, this is something I also need to fix in this version of KiCad. Can I sort them by value? Apparently I cannot sort them by value. Like, I want to sort them by value. I don't want to go through this whole thing and just assign things manually. That is just so annoying. Okay. Let's go down here to the capacitors. This would be a 603. And this would be 22, was it a 22 what? $23.20, right. $23.20. Do we even have it? No, we don't. Okay, clearly this function doesn't work in this version of KiCad. So, do we not have 2320? We have 2220. Can I see this footprint? Let's see. So, we have 2220, which looks like this. 2220. We don't have 2320. This is the one we had, so it's 2320. Let's check the data sheet of this thing. So as you can see, it takes a long time to just go over all the components and make sure that everything is correct. And even just reviewing the schematic and designing it, it takes a long time. So packing, let's see. Can we go and find the footprint? $2320 is not even mentioned here. This doesn't have any like mention of the footprint in the datasheet. And one of the things that I'm really curious about is that does it actually have that footprint if it doesn't mention it in the datasheet? Because sometimes the values they specify here are totally wrong. Like you can never trust this value entirely. Let's do a search for this particular capacitor. $2320. Can we have a PDF? Okay, it's almost like I want to just go and go ahead and find something else. 63 volts. And I don't want to pay that much for a capacitor, that's too much. Okay, so this was the only one that was a ceramic that they had in stock also. Most of them they don't have in stock. And then they have the tantalum ones, which I don't really like. And they're expensive. And then they have the electrolytic ones, and that's it. Like there is no. Okay, can we search like this instead? Let's see. So anything between 2 and let's do like this. This is a 1210. 1210 is nice. I like that. And 2220. I like that. 2220, we actually have a footprint for it even. 2225 maybe. Let's see that. 2225. There is no footprint like that. 1812. 1210. 1210 we have. So there's 7 capacitors we can use. And this is nice, you know, like look at how many we have. Like this is perfect. Like this is perfect. This is 10 microfarads, which is a little bit more than what we used originally, but they have plenty of them in stock. And these are rather small, so I like that. I like this one a lot. Let's see, let's close this one, save and exit, and let's go back to the schematic, and let's edit this to be 10. So now we're going to have a full 20 microfarads on the input. And also, since we're using the battery, we don't really need the capacitors on the input, because the battery is like the capacitors on the input are basically just going to be there to kind of suppress the variations in input voltage, which could occur if you have other things connected to the battery. But the battery is like a giant capacitor. So let's remove this one. This one we don't need anymore. Just going to delete it. And then we'll go back to this annotated. Wait a minute, did we annotate? Did it actually ask us to annotate? No, okay, yeah, they were already annotated. Yeah. Okay, cool. So this is going to be a 1210. 1210, and then it's going to be 1210. 1210. Let's see. And that was, yes, that was in inches. That's good. 1210, 1210. This would be a 603. This would be 47 microfarads. What was that? So let's see. We'll also replace this one with a 10 microfarads. 10 and 12, 10. Yeah. So this one we can remove. 47 16 volts is a 1210 actually. That's interesting. That's good. So 47 is a 1210. I like that. This is going to be 603. This one's going to be 603. This one's going to be 603 and 1210. 1210 and 603 and 603, and that would be 603, and that would be 1210, 1210 and 603. And this would be an SMC diode. So if we go to like diodes, I'm not supposed to see the capacitors there. Like, what the fuck? Seriously. By pin count. Okay. There we go. I want to sort them by schematic symbol keywords, maybe? No. By library. Yeah, that's better. So diode SMC, diode SMC, SMC. This is going to be 5 volts, 6 volt, 12 volts. So this is going to be one of those pads. So if we can go to like test pads, I guess. Sockets, resistors. What could we use? Wire pads. So there's only a single SMD pad, and the SMD pad is the 5mm pad. Let's assign that for now, and we can change it later. Battery is going to be our XT connector, so that'll be the connectors. Connector XT60. There we go. This, let's see, so the inductor, let's assign all the resistors first. So this is going to be resistors. 603, 603, 603, all the resistors are 603. Okay. TISO power pad thermal VS, like, that's interesting. So this housing, I don't think it's going to be found. I think that we need to assign this one. TPS 54360. This is an HSOP 8. Look at this. So you have like housings. The way that libraries are structured, there's like no logic in this. So you have HSOP 20 in the SOIC, and then like HSOP 36 in SOP. Can we find something that is, let's try with like housing big pads. Housing 9, okay. SATA 7, SOIC. MSOP 33. What is the housing of this chip? Let's see. Can we get a different name here? Come on. Right, so this has a, this is like a PD, so okay, power pad, plastic, small outline. So PDSO SO power pad. Where's the pitch of the pins? 1.27, okay. This could actually be the one that we're looking for, because, let's see, can we measure distance in millimeters? And then we go like this. Let's see, is grid, can we set the grid? 0.1 millimeters, so we can take there. Yeah, it's 1.27. So this is the one, and we'll just go and select this one. And in terms of inductors, we actually haven't changed the inductor here, which is important. Like beyond important. This was our 15 microhenry inductor. You see why it's important to review the schematic, because even though you go through the design procedure, sometimes you just forget to change things on the schematic. You forget to update it, so it's very important to go back later to the schematic and just go over it. So this inductor was a 6540, and we can probably just go to inductors, SMD, and we'll sort by library and by pin count. Can we find the inductor? There's so many inductors. 6540, do we have a 6540 somewhere? There's so many inductors and not enough of standard outlines. Like 1210, no, it is not there. 5050 then. Like there's 5040, there's 5050. Is this a Vishai inductor? 5050. Can we check it? Is this a Vishai 5050? This is a Barnes. Okay. What does the footprint look like? It looks like that, which is not really the same. So let's see, it's 5.4 and 2.9. Let's measure this. So this is supposed to be, no, this is not the same. This is definitely not the same. Let's see, maybe this one. Is there Borns? No, it's only like 8043. Let's see. So the only one, we have this one and then we have that one. Let's double check. This looks more like it, but I don't think it's still correct. I don't think that. It's 4.2, and because this one looks totally different. Like it's 5.4, and then there's between them is 6.8. So we have to be careful about this distance here between them. It's supposed to be 6.8, and it's like 2. So this is not it. This is totally not it. What about this one? Like in terms of inductors, KiCad is really bad. Like they don't have inductor footprints. It's so difficult. It's always so difficult to find inductor footprints. Okay, I'm gonna have to create this footprint. I'm gonna go to, let's see. I'm gonna have to create this footprint. Footprint editor. File, set active library, inductors. SMD, and let's create a new one, new footprint. What would we create? We would create this footprint here. $65.40. 6540. Let's see. 6540. Okay. And we have a pad. Put a pad there. We edit this pad. It's a pad number 1, and it has a position. Let's see. Let's set position to 0 in X, yes. In Y also. 0. Size X, millimeters. 1.7. Size Y. SMD. Yeah, that's better. Rectangular. 1.7 times 3.4. 3.4 millimeters. So, good. And then we're gonna place another pad. So we're gonna take and like duplicate this. And we're gonna place it right there. Let's edit it, and we put the pin number 2, and position X is, what is the position X? So let's see. So there's supposed to be 740 between them. What we can do is just try to kind of take this and then go there. So this is not it. This is not good. What I want to do is just I want to just actually calculate the exact distance. So I'm going to go to the calculator. I'm going to put it always on top. And what I'm going to do is set, let's see, so we have 740, 7.4, let's see, 7.4 is the total, and then actually it's going to be 3.7 plus the full size plus 1.7. So it's going to be 5.4. Let's see if that's going to be correct. So is this going to be correct? 5.4. 5.4. And then we do like this. And I press space. Let's see. Wait. So I press space, and then I can see down there what the distance is. So it's like 6.6. Now, this seems wrong. Like, what the hell? Did I get this wrong? And it looks like it's supposed to be 3.4. Okay. Let's move this out. Like that. So it's supposed to be 3.4 millimeters long. Why can't I make it 3.4? What is the problem? 3.4. No? Really? Like, really? What the hell? Okay, this is real. This is really fucked up. Like, what the hell? Only 3? Let's see, 3.4. I cannot make it more than 3. Whole shape. Okay, this is really annoying. Why is this? Maybe it's supposed to be like this. Right. Look, it's supposed to be a comma instead of a dot. I'm so used to the dot, but it's supposed to be the comma. Right, so